Hi folks, this video on alkanes is going to talk about Newman projections, a new way of viewing molecules, as well as conformational analysis. Newman projections are a useful drawing tool for alkanes to show what's known as a molecule's conformation. A conformation is the three-dimensional shape that a molecule adopts as you rotate about the single bonds. Let's look at an example, ethane. Here is a wedge and dash structure of ethane. There are many ways you can draw this, but I've chosen this one. My two carbons I've labeled as pink and blue, and notice that each carbon is tetrahedral. To draw the bonds, I show two bonds as lines, one wedge and one dash per carbon. To get to my Newman projection, I'm going to imagine taking this molecule and rotating it 90 degrees. Imagine that you're looking down the carbon-carbon bond. The pink carbon is closer to you, as are the three hydrogens attached to it. The blue carbon is right behind the pink carbon, and it has three hydrogens attached to it as well. This is my Newman projection. Newman projections are always looking down a carbon-carbon bond. The front carbon, the one closer to you, is always represented as a dot, in this case the pink dot, and then the back carbon, the one further away from you, is always represented as a circle. This is the blue carbon. I want to show you some tricks for drawing a Newman projection. In order to draw a Newman projection, you need to choose a perspective. This is denoted as an eyeball looking down one of your carbon-carbon bonds. The first thing to do is identify your front and back carbons. This is from the perspective of the eyeball. Here I've labeled these front and back carbons from this observer's perspective. The next thing you want to do is draw out any implied hydrogens on the front carbon and identify the groups and their positions relative to the observer. Because the front carbon has two lines and a wedge already, the hydrogen must be a dash. Then, and this is the hard part, you need to imagine looking at this molecule from the orange eyeball's perspective. From that observer perspective, the CH3 group is pointing straight down. The wedged bromine is pointing up and to the right, and the dashed hydrogen points up and to the left. In my Newman projection, I would have a dot for my front carbon. Its bromine would be on the upper right, hydrogen on the upper left, and the CH3 group points straight down. Next, you want to think about the back carbon. Draw out any hydrogens that aren't shown in their appropriate location, and then identify the position of the groups on the back carbon from the observer's perspective. So my back carbon already has two lines, as well as a wedged bromine, so my hydrogen needs to be dashed. Next, we have to do the tricky work of imagining looking at this molecule down the bond from the observer's perspective. From that perspective, the CH3 group is pointing straight up. The wedged bromine points down and to the right, and the dashed hydrogen points down and to the left. I would draw my back carbon part of the Newman projection as a circle representing my back carbon. The CH3 group points straight up, wedged bromine points to the right, and dashed hydrogen points down and to the left. Once you've figured out locations on the front carbon and the back carbon, you just need to overlay them to get your final Newman projection. Notice that in my original molecule, I had a zigzag shape. And in my Newman projection, my CH3 groups are opposite each other. Also notice that both of my bromines are drawn as wedged. And in my Newman projection, they're on the same side. We're going to perform what's known as conformational analysis for ethane. By this I mean we're going to imagine rotating about the carbon-carbon bond and looking at the energies of the different structures that you get as you rotate. It turns out that there are two conformations for ethane. These have different arrangements of the atoms in space. Here is one conformation of ethane. In this case, notice I have a zigzag of lines. I'm showing you the perspective that I want you to take in the Newman projection. The front carbon has the pink hydrogens on it. One of these points straight up, and the others point down and to the right and down and to the left. On the back carbon, I have a blue hydrogen pointed straight down, and then blue hydrogens also pointing up to the right and up to the left. In this conformation, there is a 60-degree angle between a blue hydrogen and a pink one. I would call this a dihedral angle or the torsional angle. These terms refer to an angle separating two planes. This conformation, in which you have the 60-degree separation of the front carbon and back carbon's hydrogens, is known as the staggered conformation. Our hydrogens are staggered and not stacked. Now let's imagine a second conformation. Rather than having lines in a zigzag, I have an up, across, down pattern of lines, and notice my wedges and dashes are all pointing up. In my Newman projection, I have both a pink hydrogen and a blue hydrogen pointing straight down, and then I have pink and blue both pointing up and to the right, as well as up and to the left. In reality, each pink hydrogen is directly in front of a blue hydrogen in the Newman projection, but I draw them as slightly off from being on top of each other just so that I can draw it in 2 dimensions. In this case, the angle between a pink and a blue hydrogen is now 0 degrees. Because one hydrogen blocks another directly behind it, I call this an eclipsed conformation. Here I've redrawn the 2 conformations of ethane, staggered and eclipsed. Here I'm arbitrarily highlighting one hydrogen on the front carbon and another hydrogen on the back carbon, and imagining rotating my carbon-carbon bond to make the positions of those pink hydrogens change. So let's imagine starting out on the far left. I start with a pink hydrogen on the front carbon up top, and a pink hydrogen on the back carbon down bottom. I'm going to imagine keeping my back carbon fixed and rotating my front carbon clockwise. As I start to rotate 60 degrees, my pink hydrogen blocks a hydrogen on the back carbon. Eventually, that pink hydrogen reaches the lower right, and this is another staggered conformation. As I continue rotating, I go back up in energy to another eclipsed conformation, then down in energy to another staggered one. Keep rotating to go back up in energy to another eclipsed conformation, and back down in energy to a staggered one. This diagram shows a full 360-degree rotation about the carbon-carbon bond. What's measured experimentally is that all of my staggered conformations are the same energy, and all of my eclipsed conformations are the same energy as each other as well. However, the staggered conformations are 12 kilojoules per mole lower in energy than the eclipsed ones. I could say my staggered conformation has a relative energy of 0 kilojoules per mole, while my eclipsed conformation has a relative energy of 12 kilojoules per mole. I want to delve a little bit more into how we analyze this number. In the eclipsed conformation, we have 3 sets of overlapping CH bonds, and my total energy in the eclipsed conformation is 12 kilojoules per mole higher than the staggered one. I can do some simple math to calculate what's the energy cost for one eclipsing carbon-hydrogen bond pair, just one hydrogen in front of another. I would take my 12 value and divide by 3, my total number of eclipsed pairs, to calculate 4 kilojoules per mole. What this means is that in my eclipsed conformation, each instance of a carbon-hydrogen bond eclipsing another carbon-hydrogen bond has an energy cost of 4 kilojoules per mole. Because I have 3 of these eclipsed pairs, that adds up to my overall 12 kilojoule per mole energy cost. I'm going to perform the same kind of analysis where I look at different Newman projections and imagine the energy of my molecule as I rotate between them. I'm going to do that again, but now with propane, a 3-carbon molecule. I'm going to first consider a conformation where I have the following wedge and dash structure. I have a zigzag line from a CH3 to a hydrogen. On my second carbon from the left, I have a wedged and dashed hydrogen pointing up, and on my right carbon, I have a wedged and dashed pointed down. From the perspective of the observer, the CH3 group points straight down, and the hydrogens of the back carbon are pointed in different directions than those on the front carbon. This is a staggered conformation. Now let's consider a different conformation where I've rotated the front carbon slightly. Notice now my CH3 group is a wedge instead of a line. And also notice that my bonds that are lined are on the same side of the molecule as each other, rather than being on opposite sides. In this case, I will have an eclipsed conformation where groups on the front carbon are directly in front of those on the back carbon. And because my methyl was a wedge, it is on the lower right. Here as well, I've labeled the methyl in pink and one of the hydrogens on the back carbon as pink, and I'm going to imagine rotating the front carbon. Here as well, I alternate back and forth between staggered and eclipsed conformations. All of my staggered conformations are the same energy as each other, and all of the eclipsed conformations are the same energy as each other as well. But the eclipsed conformations in this case are 14 kilojoules per mole higher than the staggered ones, so slightly larger than what we saw in the case of ethane. I can see from this diagram that relative to the staggered conformation, the eclipsed is 14 kilojoules per mole higher in energy. I want to evaluate this value a little more to determine why it's higher in energy than the previous example for ethane. Notice that in the case of propane, I have 2 different types of eclipsed interactions. I have hydrogens in front of hydrogens, but also a methyl in front of a hydrogen. I know from my conformational analysis of ethane that having a hydrogen eclipsing another hydrogen has an energy cost of 4 kilojoules per mole. And I have 2 of these types of interactions in my molecule. I don't yet know what is the energetic cost of having a CH3 group eclipsing a hydrogen. But I can calculate this value by knowing that my overall energy cost is 14 kilojoules per mole. I've accounted for 8 kilojoules per mole from my two sets of eclipsed hydrogen-hydrogen interactions, leaving 6 kilojoules per mole unaccounted for. This indicates that it is less favorable to have a methyl eclipsing a hydrogen compared to two hydrogens eclipsing each other. This is due to the larger size of the methyl group compared to hydrogen. The last example I want to talk about is butane, my 4-carbon molecule. There are going to end up being 4 different conformations for butane. I've drawn just one of them here. Notice that I have a central carbon-carbon bond, and the methyl groups are on opposite sides of this. This particular conformation is therefore going to be a staggered one. My conformational analysis for butane is the most complicated so far because we have methyl groups that can be in different positions relative to each other. So we could imagine starting out with the methyl groups completely opposite each other. As I rotate, I pass through eclipsed conformations between my staggered ones. 2 of my staggered conformations have my methyls 180 degrees apart, and 2 of my staggered conformations have the methyl groups 60 degrees apart from each other. These are higher in energy than the case where the methyls are 180 degrees apart. I also have 2 different types of eclipsed conformations. I have 2 cases on the left and right at 120 degrees, where I have methyls eclipsing hydrogens, and my highest energy point of my whole diagram is where one methyl eclipses another methyl. Here I've labeled these differences in energy, A, B, and C, and I've provided these energy values in kilojoules per mole. I want to highlight the different features of the 4 different unique conformations in butane. One of these puts the 2 methyl groups in the Newman projection 180 degrees apart from each other. This is known as the anti-conformation, and it's the most stable conformation of the whole diagram. Here is one type of eclipsed conformation for butane. In it, I have a CH bond eclipsing a CH bond, and 2 instances of C-methyl bonds eclipsing CH bonds. I could predict the energy of this conformation using values that I got from ethane and propane. Where you have a hydrogen eclipsing another hydrogen, that has an energy cost of 4 kilojoules per mole. Each instance of a methyl eclipsing a hydrogen has an energy cost of 6 kilojoules per mole. So I would predict my energy of this conformation relative to my most stable one. This would be 16 kilojoules per mole total. This prediction is correct, and notice that the value for A that was measured experimentally was 16 kilojoules per mole. A third type of conformation of butane is another staggered one, but where the methyl groups are now 60 degrees apart. This is known as a gauche conformation. This corresponds to energy B in my diagram above, and having the methyl groups 60 degrees apart from each other has an energy cost of 3.8 kilojoules per mole. The fourth and final conformation of butane has one methyl group eclipsing another methyl group. This is known as the syn conformation. And this is the least stable conformation. We know the energy cost of each hydrogen eclipsing another hydrogen is 4 kilojoules per mole for each instance. What we don't know yet is the energy cost of a methyl eclipsing another methyl, but we can calculate this. The overall energy is 19 kilojoules per mole. I subtract 8, 4 for each hydrogen eclipsing another hydrogen, to get 11 kilojoules per mole. This is my value for the energy penalty from having a methyl in front of another methyl. To summarize the different energy costs that we saw that having a CH bond eclipsing another CH bond has an energy cost of 4 kilojoules per mole. Having a carbon-methyl bond eclipsing a carbon-hydrogen bond has a 6 kilojoule per mole energy cost. Having 2 eclipsed methyl groups, or a carbon-methyl bond directly in front of another carbon-methyl bond in my Newman projection, has the highest energy cost we've seen so far, of 11 kilojoules per mole. And the only instance we've seen so far of an energy cost for a staggered conformation is when you have the gauche conformation, or 2 methyl groups 60 degrees apart from each other. This has an energy cost of 3.8 kilojoules per mole. So in summary, today's video introduced the idea of a Newman projection, a way of looking down a carbon-carbon bond of a molecule to describe its geometry. I talked about rotating about the carbon-carbon single bonds of ethane, propane, and butane to analyze the different shapes of the molecule and their energies, known as a conformational analysis. That's it for this video. I will see you in class.